Welcome to the latest video from iLearn Engineering. Today I'm going to do something slightly different. I'm going to be looking at how to calculate reaction forces. However, rather than doing it for a beam, as is the case with many examples, I'm going to look at a whole aircraft structure on a runway, and we're going to see if we can work out the reaction forces underneath the undercarriage. So let's have a look at the example I've got here on the screen. Alright, so here is my really bad drawing of an aircraft side on, and let me just take you through here. So we've got the two undercarriages, we've got the main wing here with this represents the engine and the thrust vector here, and I've got some basic values here in the top right hand corner. So I'm going to have the mass of the aircraft to be 40,000 kilograms and the thrust being 40 kilonewtons in this example. And the idea being is that it's stationary on the ground. There is a brake on the main undercarriage, it's that one at the rear. There's no brake on the front wheel. And we're going to try and work out what the reaction forces are at the wheels with the ground when this engine starts to fire up and produce this thrust. So in order to do that, we are going to have to create a free body diagram. So in order to do a free body diagram, you must always remove the supports. So just by magic, I am removing the support, which in this case is the runway or the ground, and I'm going to replace that with some forces. Okay, and those forces are the forces that were what the floor was doing the job of, essentially. So let's put in some forces. So we have got, let's put one here. So we've got one there, and we've got one here. Okay, so those are the two reaction forces. Let's call it reaction force 1 and reaction force 2. Now, at the rear wheel, we mentioned that it had a brake, so that brake has got to do the job of stopping the vehicle, or in this case the aircraft, moving forwards, so it's resisting the thrust. So where it comes in contact with the ground, there must be a force. Shall we call it B for braking force? There's no brake on the front wheel in this example. And we have got a thrust there given, so we can put that on, can't we? That's thrust there, so the T there equals 40 kilonewtons. And I'm also going to have to put some measurements on here in order to do some calcs. So let's look at that. So let's look at this value here. This in the middle here, we've got what is representing the center of gravity of the aircraft. So that's where the mass is taken to act from. So let's have that in a slightly different color from everything else. So let's have this one acting down. So that is the weight, which equals mg. Okay, g is taken as the acceleration due to gravity at the surface of the Earth, and we'll approximate that to be 9.81. I'll write it down here. Oops, 9.81 meters per second squared. Okay. We just need some dimensions on, like we said, so let's put those on now. So the distance from the ground to the thrust vector is taken to be 1.5 meters. The distance from the front wheel to the center of gravity we are going to take as being 9 meters, and the distance from the center of gravity to the rear main wheel we're going to take as being 0.5 meters, half a meter. Okay. So there we've got our dimensions on, our values, and we can start to do some calculations. So we want to try and calculate what are the reaction forces at the wheels. So let's scroll down and start to look at that. So the first thing we might want to do is resolve forces in the vertical direction. So let's write that in here. So here we go. So if we resolve vertically, with upwards being positive, then we can say, starting from the left, we've got R1, and then we move across to the right, we've got weight coming down, so we can say that's minus W, and then we've got a plus R2, haven't we, because that's also acting upwards. And all of that has to equal 0 because this is a static problem, and just to remind you, if you've not seen any of my previous videos, the basis behind all of this, I'll just do it in a different colour up here in the margin, is that if you sum the forces in any particular direction, say x, then that will equal the mass times the acceleration in that particular direction, x. There's not going to be any acceleration because it's a static problem, so the accelerations are 0, and so therefore the right-hand side of this equation is 0. So if you sum up the force in any particular direction, they should equal 0 for a static equilibrium problem. So this here on the left, all this business here, that's me summing up the forces in the vertical direction, if you like, in this case, and then we're setting them equal to 0. Okay, now we need to, and if you look at that, we've got 3 unknowns in one equation, so we're going to need some more equations. Let's resolve horizontally. It's fairly straightforward to do that because there's only one force, one reaction force in the horizontal and one applied force in the horizontal, which is the thrust. So we can easily write down an equation for that. So let's try that. So let's take left to right horizontally as being positive. So we can set the brake force minus thrust, which is 40,000, has to equal 0, and so from that we can therefore deduce that the braking force must be 40 kilonewtons. Okay. Now we're going to have to do some moments now to get another equation out of this. So you can take your moments about any point you like in principle. If you are clever about it, then you should take your moments about a position at which one of your unknown forces acts. So our unknown forces act at the main wheel, the front wheel and the back wheel. I was going to call it that. So if I take moments about the front wheel, that would eliminate the R1 from the equation. So I'm going to do that. So I'm going to scroll this down, and we are going to take moments. We're going to take moments about the front wheel. So let's write that down here. So let's take clockwise as being positive, and this is going about the front wheel. So the front wheel. All right, let's scroll up and have a look. Remind ourselves, what have we got here? Well, we know that we've got R1 pointing up. Okay, well, that acts at the wheel, so that's not going to be in our equation. But what other forces have we got? Well, we know we've got the weight, W, that acts down. That's 9 meters away in a perpendicular sense from the front wheel, and that's going to therefore produce a turning moment, okay? A turning moment about that front wheel. So I can sketch that on the diagram if you like, just so you can see. So it's going to have the effect of doing that particular force, all right? I'll take that off because it's just complicating the diagram, but just so to demonstrate it. So let's write that in as an equation. So we've got 9, which is the distance, times the weight. So that's the force times the distance. That's going to give us a clockwise positive moment. And then the other forces are going to be the opposite. So we can take, which one would you like to do next? We could take the thrust vector, if you like, the thrust vector multiplied by the 1.5 meters. That is going to give us a moment in the opposite direction. It's going to sort of tend to want to do like that. Okay. So let's write that in. So we've got minus 40,000, and then the distance was 1.5 meters, isn't it? Okay. And then we've got another force, the R2 reaction force, that is also going to produce a moment about the front wheel, because that has a distance of 9.5 meters away from it. Okay, so that's also going to tend to push the back up, if you like, produce a negative, in this case, moment. So it's going to put in minus R2, and then the distance is 9.5. And all of that has to equal 0. So again, I'll just show you what I'm doing there. So all of this business here on the left, that is me summing up the moments in this case about the front wheel and setting them equal to 0 because it's a static problem. Okay, right, well we can substitute some numbers in there, can't we? Because we know what the weight is. The weight is mg, we know what the mass is, 40,000 kilograms. So we can start putting some numbers in, so let's do that. So we have got 9 times the mass, which is 40,000 kilograms, times g, which is 9.81. Okay, so that's the 9w. And then we can take these other terms, these minus terms to the other side, so we can say that equals, and then we've got 40,000 times 1.5, well, that's 1.5 lots of 40, which is 60, so that's going to be 60,000. I could write that as 60 times 10 to the 3, might be a bit easier. And then also we've got plus, take the other 9.5 or 2 to the other side, so 9.5, oh, it's 9.5, isn't it? Let's back that up a bit. 9.5 R2. Okay, so we can work all that out if you like. So we bring up our calculator here. I bring this up on the screen for you to see. Clear this off. So we've got 40,000 times 40,000 times 9.81, and it's also times 9. Okay, so that is 531,600. And that equals the right hand side, which is still the same there. I've got 60,000 plus this 9.5 R2. So therefore we subtract that now, so we get to this one here, and we subtract 60,000, we get 347,600 equal to 9.5 R2. And so therefore if we divide both sides by 9.5, then we're going to get our answer for R2. So divide that by 9.5, and we get our answer there, which is 365,431. So it's 365,431 newtons. Oh, it's approximately 365 kilonewtons, isn't it? So we'll just put that as approximately 365.4, if you like, kilonewtons. And that is the reaction force at the rear wheel. And now we've found that, we can easily work out the other reaction force. Could we just take our first equation there? So rewrite that in. So if we take this first equation, R1 minus W plus R2 equals 0. So let's write that in and rearrange it the other way around so that we could take the minus terms to the right hand side. So R1 equals W, and the R2 term is minus R2. Okay. And we know what the weight is. It's our mg, isn't it? So this is mg here. So weight mg, so 40,000 times 9.81, and minus this value that we've just worked out previously. Okay, and if you do that, I did it earlier on, save me type it into the calculator again, and that will come out as approximately 27.4